In the year 1640, Fermat conjectured the following relationship. For every prime p, take any other natural number, raise it to the power of p minus 1, and you will get 1 mod p. It's one of the strange and non-obvious relationships, and Fermat couldn't prove it. It was considered a gem in number theory, no special use. But it so happened that very recently it became extremely useful. The advent of e-commerce and secure communication between strangers on the internet is to a large extent based on this. The Fermat theorem. Now what's interesting for us to note, that it took almost 100 years to prove it. It was the Swiss mathematician Euler who proved it in 1736. And in 1760, Euler has generalized Fermat theorem to the following, saying any two numbers a and n that are coprimes, greatest common divisor is 1, satisfy this relationship where this phi of n is called Euler function, is a function that counts how many numbers smaller than n are coprime with n. And that's the relationship that he arrived at and proved. This is even more strange than the original one, and more non-obvious. And when we first look at this and we are challenged, can you prove it? It looks like, how would you start proving it? How would you approach something like that? Yet, and that's why I focus on this, this critical insight, which was conjectured and laid unproven for almost 100 years, eventually, when we look at the proof, we wonder, it's so easy. How come nobody thought about it earlier? It takes 2 minutes to show it, and we will do it in a minute. The cryptographic lesson from this is that mathematics is full of surprises. When you think something is intractable and difficult, as we believe the ciphers that we use are, they can hide a tunnel that will allow somebody smarter than we are to breach them, to compromise them. Now, let's see how we prove something so strange. Okay, so let's see how we can prove Fermat, or rather Euler, theorem. That's the theory. A to the power of phi of n equals 1 mod n, as long as a and n are coprimes. Now, we take n, any natural number. It defines a list of residue, which are the numbers from 0 to n minus 1. They represent all the possible results of x equals a residue mod n, and the residue will be one of the number from 0 to n minus 1, no matter what x is, by definition of mod. Now, among those 0 to n minus 1, there are a few who are coprime with n. How many? Phi n. Because phi n is defined as the number of numbers that are coprime with n. So we mark them, R1, R2, R3, Rt. We call T, just for simplicity, the value of phi n. So phi n equals T. So it will be easier to write. R1 to Rt are those numbers that are coprime with n. Depends on what n is. If n is a prime, then all the numbers up to n minus 1 are all coprime with it. If it's a composite, it's fewer. But in any case, we can always define the list or the set of R1, R2, up to Rt, the numbers that are coprime with n. And now we take any number a such that GCD an equals 1, meaning a and n are coprime. And then what we do is very interesting. We build this set, a times R1, a times R2, a times Rt. And we ask ourselves, what is the value of one of those, a, r, I runs from 1 to t, mod n? The result is some zi. Now, Euler observed that zi must be one of those values, must be a member of this set. Why? Because Ri is coprime with n, by definition. A is coprime with n, by definition. So Zi has to be coprime with n. And if it's coprime with n, then Zi belongs to this set. Not here, not here, not here. Cannot be one of these numbers. Has to be a member of this set. So the conclusion is that Zi is some Rj. We don't know which one, but a member of this set. And then Euler asked himself, what happens if I compare for I not equal to j? Is it possible that two of those residues will be of same value? Could Zi equal Zj? Well, Zi is Ari, Zj is Arj, mod n. Now they cannot be equal if I is not equal to j, because we can cancel this and it shows that Ri equals Rj. So here comes this insightful conclusion. All those residues are a member of this set. And it is a matching of 1 to 1. So there are no two residues that reflect the result of two different R's. And as a result, the values in the set AR1, AR2, AR3, ART equals this value. It's not that R1 is AR1 and R2 AR2, but those numbers are exactly as those numbers in a different order. But the contents of these two sets, the sets of the residues that are coprime with n, and the set that is constructed from this set times A, those two sets have the same contents. That means that if I multiply all those numbers, and I multiply all these numbers too, I get the same result. So let's write it down. AR1 times AR2 times ART equals R1 times R2 times R2 RT mod n. Or, rewriting it, A to the power of what? T equals 1 mod n, because the R's, they cancel out. And what's T? T is phi of n. That's it. How long did it take? 2, 3 minutes? And it took almost 100 years. More. for all the brilliant mathematicians of the 17th and 18th century to come up with this proof. Math can be embarrassing. And we should remember this when we sign off on mathematical intractability ciphers and say, there is no mathematical shortcut here, we don't see it. It may be that there is one, and just that we don't see it. And if our adversary has a little bit more imagination than we do, we may be in trouble. That's the profound lesson from this elegant and simple proof of this strange theorem. Something to think about.